Hello, this is Professor Roman. Let's continue the ring theory lectures. We've been discussing Euclidean domains, and I want to talk now about a very interesting concept that I think, will not see too often in elementary treatments of ring theory, and that's called a universal side divisor. This concept is quite useful in understanding the issue of uniqueness of quotients and remainders, as well as for other reasons. To begin, a bit of notation. For any commutative ring R, we'll set U0 or U0 of R, when we need to mention R explicitly, to be the set R star union singleton 0. So this is the set of all units of the ring together with the 0 element. Now, here is the definition of a universal side divisor, and it applies to any commutative ring, R. A non-zero, non-unit A in R is called a universal side divisor if for any B in R there exists Q and R satisfying B equals QA plus R, the usual division algorithm, where R belongs to U0. So R is either 0 or a unit. Another way to say this is to say that every element of the ring is no more than a unit away from some member of this set RA, the multiples of A. Okay. If that's of help to you, terrific. If not, don't worry about it. You stick with this definition. Universal side divisors are irreducible. In the first place, by definition, they're non-zero non-units. But if X is a universal side divisor and can be written as a product YZ, then there exists Q and R for which Y equals QX plus R, where R is either 0 or a unit. If R is 0, then X divides Y, but Y divides X, so X and Y are associates. So Z is a unit. On the other hand, if R is a unit, then R is Y minus QX. We can replace X by YZ and factor, and this tells us that Y is a unit. So one way or the other, one of these two factors, Y and Z, is a unit. Therefore, X is irreducible. I'm going to leave it for you to show that if X is a universal side divisor, so is any associate of X. A couple of examples. In the ring of integers, the only universal side divisors are positive and negative 2 and positive and negative 3. To illustrate that 3 is a universal side divisor, we can, for any A and B and Z, there's a Q for which B equals 3Q plus R, where R is either 0 or positive and negative 1, and that is U0. And I'll let you ponder that. It says in words that every integer is within a unit of the multiples of 3. Another example, in the Euclidean domain F square bracket X, the polynomial ring, the only universal side divisors are the non-constant linear polynomials. For if little f of x is a universal side divisor, then there are polynomials q of x and r of x for which x equals q of x, f of x plus something that's either 0 or a unit, in other words, a constant. But this can't hold unless f of x has degree 1. And if f of x is ax plus b, where a is not 0, so this has degree 1, then dividing any polynomial p of x by ax plus b leaves a constant remainder. So f of x is a universal side divisor. Now we can find universal side divisors in any Euclidean pair R delta, provided that R is not a field. Because then if R is a field, then every non-constant element is a unit. And so by definition, there are no universal side divisors because they're non-units. So suppose that R is not a field, and this is R delta is a Euclidean pair. And suppose further that the image of delta, remember delta maps R to the natural numbers. Suppose the image of delta is this set of natural numbers in increasing order. And let R sub k be the set of all elements whose norm is n sub k. We've seen that R naught, the set of all elements of minimum norm, are the units, R star. Since we're assuming R is not a field, R1, the set of elements that have norm little n1, is non-empty. And if A is in R1, then for any B in R, the division algorithm tells us that the remainder is 0 or has norm less than the norm of A. Or in other words, R is 0 or R is, it belongs to R naught, it's a unit. Okay? And so in summary, the elements of R1, the elements that have norm N1 here, are universal side divisors. So in any Euclidean pair where R is not a field, we have universal side divisors. Summary, fields do not have any universal side divisors. If R is not a field, then for any Euclidean pair, the non-zero, non-unit elements of R that have smallest norm, that would be R, capital R1, are universal side divisors. But we saw in an earlier example for the integers that if we take the integers under the absolute value norm, this Euclidean pair, positive and negative 3 are universal side divisors. They don't fit. They're not in R1, they're in R2. Because their norm is not the smallest possible. That's reserved for positive and negative 1. Absolute value is 1. Here, absolute value would be 2. Here, absolute value would be 3. So we get universal side divisors by looking at R sub 1, but we don't get necessarily all of the universal side divisors. Now we can discuss the question of the uniqueness of quotients and remainders in a Euclidean domain. First of all, if A is non-zero and we write QA plus R equals Q prime A plus R prime, then of course R equals R prime, if and only if Q equals Q prime. That tells us that remainders are unique if and only if quotients are unique. So either both of them are unique or neither one. So we're trying to determine when we have uniqueness of both quotients and remainders. All we have to do is find uniqueness of either one, and we can simply refer to this issue as the issue of uniqueness. So let's suppose that uniqueness holds in a Euclidean pair, R delta. If A, B, and A plus B are all non-zero, this latter means that B is not the negative of A, then we can write A as 0 times A plus B plus A, but we can also write it as 1 times A plus B minus B. So, if A and negative B are remainders, that is, if their norms are less than the norm of A plus B, then uniqueness fails. Obviously, the quotients are different, 0 and 1. So uniqueness will imply that if A, B, and A plus B are non-zero, then delta of A plus B must be less than or equal to the maximum of delta A and delta B. It's not easy to get a handle on the norm of a sum, but this is one instance where we get some information. Uniqueness of quotients and remainders implies this condition. To see that this condition implies uniqueness, suppose that we have a non-zero element A, and we have Q1A plus R1 equals Q2A plus R2. Now we're assuming that condition. I don't know that there's a name for this condition. Norm of some inequality or something like that. And we want to show that R1 equals R2, which will then show that Q1 equals Q2. We know that Ri is 0, or its norm is less than a norm of A. So to show that R1 equals R2, assume they're different. If R1 is 0 over here, then A divides R2, and R2 is not 0. So norm of R2 is strictly less than norm of A. That's from here, and that's less than or equal to norm of R2 because of this, and that's false. And so, by a little bit of symmetry, we can assume that neither remainder is 0. Then we can write this equation like this, and so norm of A less than or equal to norm of R2 minus R1. Here's where we use the uniqueness condition, less than or equal to the maximum of norm R2 and norm R1. But these guys have norm less than norm of A. And again, this is false. So R1 must equal R2, and we have uniqueness. And so this norm of some inequality, or norm of some upper bound, is equivalent to uniqueness of quotients and remainders in a Euclidean pair. This uniqueness condition has an interesting consequence. I'll go back. Here's the condition. Has an interesting consequence when we apply it to units. If u and v are units and u plus v is not 0, then the norm of u plus v is less than or equal to the maximum of the norm of u and norm of v. But if u and v are units, these are the minimum norm. Remember, all units have the same norm, and it's the smallest possible norm. So we can say that's equal to the norm of 1. Therefore, since u plus v is not 0 and has norm less than or equal to the minimum norm, it must in fact have minimum norm, and so it is a unit. This is equivalent to saying that u naught is closed under addition, and that's enough to make it a field. It's closed under multiplication. It has 0, it has 1. I'll let you check the rest. It is a field. So let R delta be a Euclidean pair, then quotients and remainders are unique if and only if this condition holds, this inequality on the norm of the sum. Furthermore, uniqueness implies that this set is a field. Now we have enough weapons to determine which Euclidean pairs possess uniqueness of quotients and remainders. If we look at some familiar Euclidean domains, we can find 2 such cases of uniqueness pretty easily. If R is a field, say call it F, then all the non-zero elements are units. And so any Euclidean norm on F is constant. It takes the same value on all the units. So it's constant on the non-zero elements of F. It's not defined at 0. Therefore, for any A and B in the field with A not 0, we can write this, where R is 0 or norm of R is less than norm of A. But that's not possible if the norm is constant on all the non-zero elements. So R must be 0. So all the remainders are 0, and therefore, of course, remainders are unique. The other case is the Euclidean pair f squared bracket x, the polynomials over a field f, with the degree norm. As to uniqueness, if we write this equation, where R sub I of x is 0, or its degree is less than the degree of p of x, we want to show the remainders are equal and the quotients are equal. Then rearranging, we have this, and comparing degrees, we see that this is possible if and only if both sides are 0. The degrees just do not match. And so uniqueness holds. And with a slight tweaking of this argument, it will also hold, uniqueness will also hold for the polynomial ring and the norm f composed with the degree function, as long as f is strictly increasing. So we can now say that uniqueness of quotients and remainders holds in a Euclidean pair R delta in the following cases. R is a field, or R is a polynomial ring over a field, and the norm has the form f composed with a degree function, where f is a strictly increasing function on the natural numbers. This is not an if and only if. It just says these are 2 cases where uniqueness does hold. So the question naturally arises as to whether there are any other Euclidean pairs for which uniqueness holds. And universal side divisors will be the key to giving us an answer to that question. And here is the reason. Let R delta be a Euclidean pair in which uniqueness holds. Then any universal side divisor Z, and we know such exists, any universal side divisor Z is an independent variable in this ring U0 with Z attached. This is the smallest subring containing U0 and Z. And by independent variable, what we mean is if you have a polynomial in Z equal to 0, all the coefficients have to be 0. So there's no algebraic relationship among the powers of Z. Or you might say a different way, there's no polynomial, non-zero polynomial satisfied by Z. We can also say U0 square bracket Z is ring isomorphic to the polynomial ring U0 square bracket X, where X is a variable. Okay. Z is an element of R, but what this theorem is saying is that it acts just like an independent variable X. The proof is what? 4 lines? We can assume, for the purposes of contradiction, that R0 is not 0. If R0 were 0, it would go away. We could cancel a Z and basically start over with a polynomial of degree n minus 1 equals 0. So we may as well just assume that R0 is 0 to start with. So R0, which belongs to U0, if it's not 0, must be a unit. So R0 is not 0, but it is equal to this when we move everything else on the other side of the equal sign. And that tells us that the norm of Z is less than or equal to the norm of R0, which implies that Z is a unit. Or, frankly, just looking at this is a unit, so Z must be a unit. And that's false, because Z is a universal side divisor, and so it's not a unit. Now we can show that uniqueness of quotients and remainders in a Euclidean pair, let's change that to pair, implies that either R is a field or R is a polynomial ring, and the norm has this form. So when I said before this was not an if and only if, this just gave us 2 cases of uniqueness. Turns out that that is all the cases of uniqueness. So all we have to do, in a sense, is assume that R is not a field and show that it must be a polynomial ring, and the norm is what we might call an inflated degree function. We have a theorem that tells us that R has a universal side divisor, Z, and that element has minimum norm excuse me, among the elements of R that are not units, the non-zero elements that are not units. But that norm is strictly larger than that of all the units, the non-zero elements of U0. It's the second largest norm. And we've just learned that U naught of Z is a polynomial ring. So our goal then is simply to show that every element of R belongs to this polynomial ring, this subring of R. Or every element A in R is a polynomial in Z whose coefficients come from U naught. They're either units or zero. Well, to begin, we'll divide A by the universal side divisor Z, and we get this. U naught, R naught is in U naught. Well, Z is not a unit. And so Q naught properly divides Q naught Z, and so delta of Q naught is less than delta of Q naught Z, which is delta of A minus R naught. Let's move that over. And now, if R naught is 0, that's just delta of A. If R naught is not 0, we apply the uniqueness condition, and this is less than or equal to the maximum delta A and delta of negative R naught, which is the same as delta of R naught. R naught's a unit, so this is the norm of a unit. That's minimum norm. So this maximum is also equal to delta A. So delta Q naught, norm of Q naught, is less than, strictly less than, that's important, the norm of A. Now, something I could have said before we went through this is that if Q naught is also in U naught, R naught is, then we're done, because we have A as a polynomial in U naught of Z. If it's not, however, what do we do? Well, we divide Q naught by Z. We get this expression, which we can then plug into this one. And we'll now have a polynomial of degree 2. A is written this way. But we also have to keep track of what's happening to the Q's. We've already seen that the degree, or the norm of Q naught was less than the norm of A. The norm of Q1 is less than the norm of Q1Z. This is the same as what we just did with different symbols, which is equal to the norm of this difference. Same inequalities here. So norm of Q1 is less than norm of Q naught. So we get this, we get A as a quadratic polynomial. Again, if Q1 belongs to U naught, we are done. A is a quadratic polynomial in Z over U naught. If not, we do it again. We divide Q1 by Z. Now, the reason we're tracking the norms is because we don't want to make sure this can't go on forever. But we've already seen delta Q naught is less than delta A, delta Q1 less than delta Q naught, and this will continue. So what's happening is that the leading coefficients in these polynomials have strictly decreasing norms. Eventually, then, the leading coefficient has to be a unit. And A is indeed a polynomial over U naught of Z. Okay? An argument well worth going over. Finally, we want to take a closer look at the norm function. Well, one way to do that is to notice that the same degree equivalence relation says two polynomials are equivalent if they have the same degree. It happens that the norm must be constant on each of these equivalence classes. So what we can show is that if the degree of a polynomial is n, then the norm of the polynomial is the same as the norm of z to the n. And therefore, since norm of 1 is less than norm of z is less than norm of z squared and so on, it follows that delta is also strictly increasing as a function of the degree, once we've established this. So it'll look like this, where f is strictly increasing. That's what we wanted to show. So we have to prove this implication. And we can do that by induction. If n is 0, then the equivalence class we're dealing with is just the units. And we already know delta's constant on the units, and in fact takes on minimum value on that equivalence class. Value delta 1. So we can assume that this holds for a given, any polynomial of degree less than n, and show it holds for polynomials of degree n. So let p of x be such a polynomial. We need to show that of degree n, we need to show this. Well, we can assume that p of x is monic because that's just a matter of adjusting by a unit factor. So we can assume p of n looks like this, z to the n plus p naught of z, where the degree of p naught of z is, say, m less than n. So the inductive hypothesis will apply to p naught of z. Then delta of p of z is delta of this, which by uniqueness is less than or equal to the maximum of the norm of zn and the norm of p naught of z. The inductive hypothesis tells us the second norm is the norm of z to the m. This is the norm of z to the n. And since m is less than n, z to the m divides z to the n, so the maximum of the two norms is delta zn. So we know at least, we're trying to show delta of p of z is delta of zn, but we know at least it's less than or equal to. But then delta of zn is delta of this difference, which is less than or equal to the maximum of the deltas. Again, this is delta of zm. And this one is delta of zn. Because of this relationship here, this is a less than or equal to. So I'm replacing delta p of z by delta zn, but I have to put less than or equal to. Again, this maximum is delta zn. Because these two are the same, we have equality throughout. Okay. So the maximum of delta of p of z and delta of z to the n, m, is delta of z to the n. But this one is smaller than this one, so this one must equal this one. And that's what we wanted to show. I realize that some of these arguments are a little abstract and may take a little getting used to. Don't worry if it's all kind of vague when you first go through it. A little bewildering. You just have to, if you're interested, you have to go through it again, maybe several times. Frankly, I rewrote this material several times, trying to find a way to explain it as clearly as I can. I don't know if it's clear or not, So there's some things to deal with here. Okay, so this is the summary. Let R delta be a Euclidean pair, then quotients and remainders are unique if and only if R is a field, in which case delta is constant on the non-zero elements. R is not a field, in which case if Z is a universal side divisor, then R is equal to U naught square bracket Z, and that's a polynomial ring. Z is an independent variable over the field U naught, and delta has this form.